It's my pleasure to introduce Erika Davies, who's going to talk about nuclear magnetic something or another, which she will in due course explain. And we welcome her from Macquarie University. Thank you, Erika.
So yeah, I was asked to come along and say a bit about what it is that I do. As Richard said, nuclear magnetic resonance. What is it? Do we need to worry about the nuclear bit? How do we do it and why? So just a little bit about me, not to dwell, but a bit of background. Basically, short version, I've been in universities most of my life and look like I'm about to leave any time soon. I have a background in software engineering, pure maths and chemistry, and worked at UNSW for a little bit doing some work with NMR, but also MRI, which is a sort of sister discipline that will become apparent as we continue on. But because MRI is in a medical context and you're dealing with lay people who maybe get a bit worried about nuclear, they just leave the N off. So in fact it is nuclear magnetic resonance imaging, but people call it magnetic resonance imaging because otherwise people would be far more anxious about going and getting it done than they are. And yes, now I'm at Macquarie and I'm looking after their NMR facility, and that pays for me to go flying, which is one of the reasons I do it, but not the only reason. So you guys don't have to listen to me blathering on all night. I have got a few little videos interspersed, and the first of them is a very high-level introduction to MRI safety, and this was produced by General Electric back in the 80s, so it's a little bit cheesy and a little bit dated, but it gets the point across quite well, I think. If it loads.
Magnetic resonance is a revolutionary technique which may prove to be as great a tool to medicine as the X-ray. Its expanded ability to see the invisible gives us new powers of diagnosis. MR is a complex and sophisticated diagnostic imaging device, but at its core is a simple and powerful force: magnetism. Magnetic force can't be seen, makes no sound, offers no warning at all that it's even there. But the MR system power is awesome, up to 25,000 times the force of the Earth's magnetic field. And how strong is that? Compare it to the power of a crane magnet, which can lift up to 4 tons of iron and steel. The field of the MR system magnet is even stronger. This tremendous force is needed for the system to do its job of aligning hydrogen atom protons, so imaging can take place. But despite its great power, the MR magnet functions like any magnet, large or small. For example, a bar magnet. Its magnetic field is revealed by iron filings. The filings align themselves along the magnetic field lines from one pole to the other. The same magnetic effect is produced by electric current flowing through coiled wire. When the electric current is increased, the magnetic force increases with it. The closer lines indicate a stronger field, and where the lines converge, the force is strongest. The MR system magnet requires a tremendous amount of electric current, up to 1,300 amps, or 13 times the current in an average household. That's why the conductor in the MR system is super cool. This removes electrical resistance in the conductor, so there is no loss of current. The supercooled conductor also means no additional external power is needed to keep the current flowing within the magnet coil. Thus, the magnetic field is almost always present. So even though the system may not be in use, the powerful force is still there. The MR magnetic field shape is the same as that of a bar magnet, pulling with the greatest force where field lines converge. And as with any magnet, the closer you are, the greater the magnetic force. How strong is the force? How would it affect some of the tools and other objects that might be accidentally brought into an MR scan room? We've prepared a demonstration area at GE's MR manufacturing facility in Waukesha, Wisconsin. You will see some experiments and demonstrations which should never be attempted outside of this carefully controlled environment. The magnetic force on an object is a function of three factors: its mass, its distance from the magnet, and how it's oriented to the field lines. What will be the force exerted on a 2-pound pipe wrench? Securing one end of a line to the wrench and the other to a strain gauge and winch allows us to measure both the force and distance from the magnet bore. At a distance of 2.5 feet, the gauge reads 3.7 pounds. Reduce that to 2 feet, and the force rises to 10.8 pounds. Now, as we get closer, the force will increase dramatically. This graph plots force against distance and shows that at close range, the magnetic force doubles or triples with just a few inches movement toward the magnet. And finally, at the magnet, this 2-pound wrench is pulled with a force of more than 50 pounds. If the wrench should slip at this point, how fast would it fly into the magnet? For this experiment, we'll take a rubber ball filled with steel shot and toss it into the magnet. A radar gun will indicate the speed. In these tests, we measured speeds of 20 miles per hour or more. But more important is the rapid acceleration and unpredictable direction. The ball can take any number of routes as it flies into the magnet bore. Imagine the damage that could happen if this were a wrench, oxygen bottle, or other sharp or heavy object bouncing around like this. And what would be the impact of a wrench accelerating into the magnet as the pulling force reaches 50 pounds or more? These demonstrations, which should never be attempted by anyone outside of this controlled environment, show the overwhelming power of the MR system magnet and the sudden violence that can result from carelessness or lack of knowledge.
Depends on mass, so you get away with it. Yeah. So something like that wrench is a scary prospect in one of these roofs. And an oxygen cylinder or something like that, even more so. You can find lots of examples of these sorts of videos online. There was one that was done by some kids at Berkeley. There was an MRI that was going to be decommissioned, so they decided to take this as an opportunity to see what would happen when you took all these things that you're explicitly told don't take them near the magnet. They, of course, took them near the magnet, including chairs and things. So you've got this office chair which is hanging in midair, being dragged into the magnet. Yes, it was not, well, there's a certain seriousness to this which I felt was not properly conveyed by that video. There are also some pretty horrific examples of medical catastrophes that have happened when you take these sorts of objects close to these magnets. So the video introduced the idea of superconductivity and the fact that you have essentially a solenoid, you're passing a current through a wire, a coiled loop, and generating a magnetic field, huge currents in this case, in order to generate very high magnetic fields. And because these are superconductors, once you have charged the magnet, once it's at field, you don't supply any external power. So one of the most common misconceptions you have to deal with when you're looking after these facilities. Contractors will come in, people from property will come in, they're wanting to do building upgrades, or they want to come in and do some work. Oh, when will the magnet be off? When can we come in? Well, you can't. The magnet is always on. We have to find some other way of dealing with this. It also mentioned the fact that the fields were in excess of the kind of magnetic field that's generated by an electromagnet in a junking yard. Those tend to be of the order of 1 Tesla. Typical MRI is 1.5 Tesla. There are some 3 Tesla magnets in use. There are also 7 Tesla MRIs, but those are for research only. They're not used clinically. And so a modern 1.5 Tesla magnet would be 60,000 times Earth's magnetic field at the centre of the bore, not 25,000. So the technology's moved on quite a bit since this video was made.
Got a question?
Yes.
On the safety aspect, how long does it take to quench the field if something happens?
Okay,
there's a fair bit of stored energy there.
Yes. If you have to deliberately quench the system, which in a medical context you do have these situations, if someone, the primary danger is the projectile effect, which is what was demonstrated in this video. So there was a fairly recent incident in Mumbai when a ward boy was told to bring an oxygen mask into the MRI room, and he misunderstood the instruction and he brought an oxygen cylinder in, a big one, and he went flying across the room. There was a technician standing in front of the magnet at the time. He ended up half in the magnet, trapped against it by this cylinder, and the ward boy, having flown across the room, had his arm trapped and broken by the impact. There is a button in MRI facilities called the quench button. It's a big red button that says "Do not push this button," unless you really mean it. It's a bit like Spaceballs. And they pressed the button and nothing happened because GE had disabled it.
Oh.
Because cryogens are expensive, and inadvertent quenches are very expensive in terms of the amount of liquid helium, in particular, that is lost when this happens. It took them, I think, 4.5 hours because they couldn't get an employee to get out there to actually override the system and force the quench. In the event that you can push the button and it actually happens, it's actually quite quick. It's a chain reaction. You'll see later on when I talk about magnets. There's a quench video which describes what the process of a quench actually is when that superconducting property of the windings is disrupted, and you get a chain reaction of heating, resistive heating throughout the windings, and then the cryogens boil off very violently and are ejected from the magnet, and that happens quite quickly, and then the field dissipates, and it's just a big can of metal at that point. Any other questions? So, my DVD isn't working. Why is my DVD not working? Oh, because I'm full screen. How do I get this back to? I'm not good with these modern things. I should have just done it on the old version. I hope that's not going to happen every time I try and play a video. I think it is though. So, yes, there's some strong fields that introduce potential hazards. So, why would we work with such strong fields if we didn't need to? That's a question that I'm going to address. I'm also going to talk about what nuclear magnetic resonance is, what we do with it, how we observe it, what hardware we actually need in order to do these experiments, and one question that may have occurred to anyone here who here has had an MRI? A few people? Yes. They're very loud, right? They give you earplugs or they give you a headset to block out the noise because the noise is quite deafening, and a lot of people are curious about what the noise is all about, so we'll spend a couple of minutes talking about that. I don't know if anyone here has seen Red Dwarf. If the answer is no, then no one's going to have a clue what I want about. So what is it? It's not a white hole. I am going to have to do a bit of maths, I apologise. But I have ripped out nearly all of it, so I hope it will be better than it was. Specifically, I'm going to be talking about nuclear magnetic resonance spectroscopy, which is what I really do. So the first thing we should probably address is the question of what a spectrum is. And if I asked someone who had no background in science or engineering to tell me what a spectrum was, they might refer to this sort of arrangement where you have white light passing through a glass prism and you get the splitting into the rainbow. If I asked one of you what a spectrum was, you might be thinking about the electromagnetic spectrum and the full range of that spectrum, going all the way from gamma rays down to long radio waves. On the other hand, if I was to ask a chemist like myself what a spectrum is, then we are always trying to identify specific bands of radiation that are absorbed or transmitted by an object and that correspond to specific structural features. So the kind of features that we might look for, and try and get out of my own way. I'm going to draw a rather complicated looking molecule. Sorry, we're not chemists. Has anyone here done anything other than high school chemistry? Yes. Okay, so we've got a couple of people, but I will pitch this as if the answer was no.
And you remember everything now.
Is there any same road as the rest of us?
I've got this on the brain because the medicinal chemistry students are busily synthesizing these kinds of compounds at the moment. Okay, so when you're a chemist, you're interested in identifying certain kinds of structural features. You might be interested in identifying a carbonyl. You might be interested in identifying the sulfonamide. You might be interested in whether or not there are any benzene rings floating around. I choose to call it a benzene ring because benzene's probably something a lot of you are familiar with and heard of, whereas if I call it its chemical, well, more usual chemical name, that wouldn't have much resonance. So when we're doing chemistry, we're looking for a way of saying, yes, we've got an aromatic system, or yes, there's a sulfonamide group, or we've got a carbonyl, and we want to know something about what kind of carbonyl. You know, there are different kinds, ketones, aldehydes, esters, things like that. So one of the kinds of spectroscopy that we do is infrared spectroscopy. And rather than me standing and trying to indicate vibrational modes, I think the video says it a lot better than I could. So in the video we have red representing oxygen, the white represents hydrogen, and the grey is carbon. So this is methanol, the one you don't drink. And these are vibrational modes of chemical bonds. So the chemical bonds that exist in molecules, they're not rigid, they're not hard, strict bonds like they are represented in these models. They actually vibrate. We can trigger these vibrations by introducing photons with the right kind of energy. And there are all these different kinds of motions that you look a bit of a fool demonstrating. The umbrella one is particularly good. Oh no, I'm getting it wrong. There we go. Bending. I was doing symmetric stretch. So you've got all these different kinds of stretches and bends and wags and all sorts of motions that the molecule can undergo. And in the background you have an example of an infrared spectrum. And as this video works through, now we've got a CO stretch, and that corresponds to a wave number of about 1000. So transmittance is on the vertical axis, 100% transmittance, we're not getting any absorption, but where we do see absorptions, this molecule is absorbing and starting to vibrate in particular ways. So we can identify certain features. Not again. Right. So typically a spectrum will be arranged according to frequency or wave number because either of those is proportional to energy. If we, this is the Planck-Einstein relation. So h being Planck's constant, the energy is proportional to the frequency, and of course that's proportional to the reciprocal of the wavelength. So, and 1 on lambda is defined as wave number. So you're going from lower to higher energies, and in this example, that's this molecule, 2-butanone, which is an industrial solvent. This one has a double bond between the carbon and oxygen, so that's a carbonyl group, like the one I drew over there, and that has certain characteristic stretching, which has been identified there at about 1700 wave numbers. And the fact that it's at 1700, not 1650 or 1800, tells us about what kind of specific carbonyl group this is. It tells us that there are carbons on either side, not an oxygen, for example, on one side. This area is pretty common to most organic compounds. You get CH stretches, so these CH bonds are stretching in here, and we get some information there. Anything from here down is designated the fingerprint region, and it's specific for a specific molecule. We don't find general group information down there. But that's an example of what we do in chemistry when we're looking at spectroscopy. So, as I said, we're trying to provide energy of a specific frequency that corresponds to some kind of transition. So in infrared, that transition is a vibrational mode. And what we want to try and establish is what that energy level transition corresponds to when we're doing nuclear magnetic resonance spectroscopy. And what is the magnitude of this energy gap? Because that's going to tell us what frequency we need to supply. And as it happens, that frequency sits in the UHF band, but we will get to that. So my next little video is a presentation by Sir Paul Callaghan, who was Professor of Physical Sciences at Victoria University in Wellington. And it's a really nice introduction to nuclear magnetism using, by analogy, with the gravitational field. So I will let Sir Paul explain. Oh, and I will start it from here.
The first principle of understanding atomic nuclei in a magnetic field is to realise that those nuclei have magnetism. And so, like little compass needles, when they're placed in a magnetic field, they tend to line up with the field. And I can demonstrate that idea with this wheel. There's no magnetic field that's playing a role here, but we have the Earth's gravitational field. And the effect of that gravitational field is that if I try to suspend this wheel on a string like this, it twists and finds a natural orientation pointing along the Earth's gravitational field. Why is that? Well, the combination of the weight force of the wheel and the string causes a torque to act. That torque or twisting force reorients the wheel so that it hangs vertically. The second idea that's really important in understanding nuclear magnetism is the idea that the nuclei themselves have angular momentum. Let me demonstrate angular momentum with this wheel. I can do that simply by spinning it. Now let's try that same trick of suspending the wheel, like I did before, on the string, now that the wheel is spinning. Something really remarkable happens. That effect is called precession. And that precession idea is very, very important in understanding the way magnetic resonance works. Let's look at that precession a little more closely and see how it depends on the orientation of the axle of the wheel. I'm going to start with the wheel with its axis horizontal. It takes about a second to go around. What happens if we orient the axle slightly differently? Like this, for example. It takes about a second to go around. In fact, it doesn't matter what orientation we have this axle, the precession frequency is pretty much the same. However, if we do suspend the wheel in that natural low energy position, the precession is very, very hard to see. If we tilt it a bit, it reappears. So we have to have the axle of the wheel tilted from the vertical in order to see the precession. By the way, there's another position where the precession is very hard to see as well, and that's with the axle pointing up like this. But anywhere in between, pointing up and pointing down, the precession is very visible. By the way, these two states of pointing down, pointing up, turn out to be very relevant in the case of the atomic nuclei that we'll be looking at in these series of videos, and that's the hydrogen nucleus. It turns out that the hydrogen nucleus has two very natural states in a magnetic field, one pointing one direction and one pointing in the other direction. So what have we learned here? We've seen that in order to observe the precession, we need to have the axle tilted at some angle away from the vertical. And that begs the question, if we did start in that low energy position with the axle pointing vertically downwards, how could we disturb it in such a way that we could make the precession visible? And I want to demonstrate that to you. Just watch this trick. I did it. I used my finger to apply a torque to the wheel that brought the axle away from the vertical position into the horizontal. What was the basic idea behind the trick? The first thing is that I had to apply the torque in the horizontal plane. I had to apply it in a direction normal to, or at right angles to, the torque that the Earth's gravitational field is applying. The second thing is that I had to move my finger around in synchrony with the wheel, keeping the reorientation of that torque from my finger at the same frequency as the precession frequency. Let me just demonstrate that again. So this movement of the torque following exactly the precession frequency of the wheel is known as resonance. The frequency is exactly the same in both cases. And the idea of resonance is really central to what we'll be looking at when we reorient atomic nuclei from their natural equilibrium states in a magnetic field. So that's wheel mechanical resonance. When we perform nuclear magnetic resonance, we have to do the same trick. We have to apply a torque that's orthogonal to the torque of the magnetic field on the spins, and we have to have that torque varying with time or oscillating in exact frequency match with the natural precession frequency of the nuclear spins. And how do we apply that torque? We do it with another magnetic field. A magnetic field that's orthogonal to the main magnetic field that tries to orient the spins, and a magnetic field that's oscillating in time in exact synchrony with the precession frequency of the atomic nuclei. And that is nuclear magnetic resonance. There's one more thing I want to show you. Let's go back to the wheel. Suppose we do this wheel mechanical resonance and end up with the axle pointing in a direction that really shows the precession very nicely. The horizontal orientation as shown here. Let's look what happens with time. Gradually, the wheel reorients and the visibility of the precession starts to die away. This returning to some sort of equilibrium is something we'll also see happening with atomic nuclei.
That's what happened to us.
Hmm? That's what happens to you with the magnet. Yes. You're all just wheels. Right, so it's a really good analogy for what's happening at an atomic level. But the key points at this stage are the fact that most nuclei have an intrinsic property known as spin. And so they behave like tiny bar magnets. And that magnetic moment we represent as mu. And mu is proportional to this nuclear spin angular momentum. And the proportionality constant is gamma. Gamma is called the gyromagnetic ratio. It's unique for every nuclear species. And the magnitude of gamma gives you some idea of how strong this little bar magnet is and how strong the interaction will be with an applied field. So they do apply with they do interact with applied magnetic fields. I'm going to refer to the static magnetic field that will be generated by our superconducting magnets as B0. And that's typically in the Z direction, represented in the Z direction. That's for an NMR spectroscopist. For an MRI person, of course, the magnetic field is horizontal, in line with your body when you're lying in the magnet. But we're talking about NMR for the moment. And the energy of the interaction between these tiny little bar magnets and that applied field will depend on the specific nucleus. It depends on that gamma, and also on the magnitude of the applied field, so the magnitude of B naught. Now, as Paul Callahan was saying, you've got these natural states. You have, in terms of the wheel in the Earth's gravitational field, you have the wheel pointing down and the wheel pointing up as minimum and maximum energy states, if you like. When it comes to an applied magnetic field, the minimum energy configuration is for the spin to be in line, to line up, like a compass needle in the Earth's magnetic field. It lines up with the field. So we're talking about magnetism now. The lowest energy configuration is for the spin to align itself with the field. And we call that the spin up state or the alpha state. On the other hand, we could have the spin in direct opposition to that applied field. So in that case, we have maximum energy, and that's called the beta state or the spin down state. And the difference between these minimum energy and maximum energy states, that delta E, that's going to tell us what frequency of electromagnetic radiation we need to supply to excite transitions between these levels. And in fact, that's given by this equation, h bar gamma B naught. H bar is just Planck's constant on 2 pi, so we're talking about a hertz rather than a radian per second frequency. So that's the relation I had up on the board before, and we refer to this frequency as the Larmor frequency, and that's the most important thing in NMR or MRI. The Larmor frequency is fundamental. That's the natural resonance frequency of a particular nuclear spin. All right. So some examples of commonly studied nuclei would be hydrogen. We look at 1H, the proton. We look at carbon-13, nitrogen-15, fluorine-19, and phosphorus-31. The natural abundance of these species is given here, so it's very easy working with hydrogen or fluorine or phosphorus. It gets a bit more challenging with carbon, and it becomes even more difficult with nitrogen-15. And the relative sensitivities are given here relative to hydrogen, hydrogen being the most, well, of commonly observed spins, the most sensitive. And here are the Larmor frequencies, the resonance frequencies of these nuclei at 9.4 Tesla. So that's a typical, it's fairly low end these days, a 9.4 T magnet. So remember, the electromagnets in junking yards are 1 T. So these are about 10 times the strength of an electromagnet in that context. So hydrogen, 400 megahertz, carbon, 1/4 of that. The gyromagnetic ratio of carbon is 1/4 of that of proton, and so on. So these frequencies are all sitting in the UHF band. So this is why when you...
No, they're not.
They're not?
Definitely not 100 megs or 40 megs or 160.
All right, the low end. All right, fine. They're radio frequencies anyway, and they're in the sorts of bands where you might expect to hear radio, the kind of radio that we listen to in the car when we're driving. So
that we talk on.
or that you talk on. So this is why when they build magnet rooms in hospitals, they have to shield them, because there's a lot going on in these frequency bands, and you can get a lot of interference when you're trying to do imaging from everything else that's going on, which you really don't want coming in and bombarding. The signal from NMR is really, really weak, so it's going to get drowned out by all this if you don't have a lot of shielding. And yes, I'll just highlight nitrogen. Nitrogen's a pain, and as you pointed out, it's low frequency, and that is actually a problem for us.
On the shore of Osprey near Channel 2.
All right, so I'd like to go back to what was being described in the video in terms of precession around a static field. But before I can do that, I need to introduce this idea of bulk magnetization. So up until this point, we've just sort of been talking about individual spins, but that's not what we're looking at when we're looking at, say, a human body in an MRI machine. You've got human tissue, which has got countless nuclei in it. So you're not looking at what's happening to individual spins, you're looking at what's happening to an average. You're looking at an average. You're looking at a spin ensemble, if you like, and an average effect. So if you don't have any kind of field in place, then these little tiny nuclear bar magnets, there's no preferred orientation. They can be in any orientation. You've got thermal variations, so they're just going to be in a random distribution. And if you were to add all those little contributions together, you've got a tiny magnetic field from this nucleus and a tiny magnetic field over here. And if you added them all up, then the net effect would be 0. I don't know if people remember vector addition, but if you have a vector there, another vector, you want to add them together, the resultant would be going from the start of the first vector to the end of the second vector. So you can do vector addition, and in the case of no applied field, in the case of no energetic preference, you're just going to have no bulk magnetization. When you put your sample of interest into a big static field, nothing happens immediately. This isn't an instantaneous process. You don't put your sample in the magnet and instantly they all go one way or the other and line up. It's a gradual adjustment. It's a very weak interaction energy. The bias is very slight. So you put your sample in the magnet and then you wait. Typically only a few seconds, but you do have to wait, and gradually you get this build-up. There will be a slight energetic preference for the spins to be more oriented with than against the field. And so gradually a bulk magnetization vector, an average of all of these little spins, will start to emerge in the Z direction, in the same direction as your applied field. There's no component in the X and Y plane because there's no energetic preference in the X and Y direction. We are applying our static field in the Z direction only. So we get a very slight bulk magnetization that we can manipulate. Now, the signal intensity that we get when we're measuring our NMR signal is a function of the size of this vector. So we need to find ways of making that bigger. We need to make it more favourable to be in line with the field than against. And the way we do that is by increasing that energy gap. And that requires us to increase the applied field. We can't change gamma. Gamma is an intrinsic property of a nucleus. It's fixed, it's constant. We can't do anything about it. It is what it is. But the Larmor frequency was given by gamma B naught. Now B naught is something we can do something about. So this is the motivation behind working with these really strong magnets. You want to try and make this bulk magnetization vector as big as possible. And at present, the strongest field that's active in science, in the scientific community, is about 23.5 Tesla, which is 470,000 times the Earth's magnetic field, and it's about a gigahertz for a proton nucleus. We tend to talk. We don't tend to say, oh, this is a 9.4T magnet, or this is a 14T magnet. We'll say, oh, this is a 400 megahertz, or this is a 600 megahertz. We refer to magnets by their proton resonance frequencies. It's one of the many abuses that goes on in this field. All right, so this is a terrible drawing. I apologize. I'm a scientist, not an artist, so this is the best I could do, I'm afraid. This wiggly, it's supposed to be three-dimensional, but it doesn't look very three-dimensional. That's supposed to be a coil along the x-axis. And we've got our bulk magnetization sitting in line with the z-axis, and that's where our applied static field is. So if you remember back to the video, when that wheel was spinning in line with gravity, then you couldn't really see the precession. So in this configuration, we can't see any precession. That bulk magnetization is just sitting there in line. So we need to tip it away from that axis. And in the video, Paul Callahan did that by using his finger. He applied a force perpendicular to the main field, gravity. He applied a force perpendicular, and he applied it in synchrony, so with the natural precession frequency. So how we do that in in NMR, we pass a current through the coil, we generate a little magnetic field B1, and that field, because of the arrangement of the coil, that field is going to be in line with the x-axis. So it's going to be orthogonal to the main field, which is what Paul Callahan described when he was talking about the wheel. We have to apply this force perpendicular or orthogonal to the main field. And this, because this magnetization is perpendicular, we're now going to get a precession of that magnetization around B1. So it will start to spin this way because it's now seeing this B1 field. So I've tried to represent that with a disc. And so your bolt magnetization is starting along Z. You have B1 in that direction. If you remember your right-hand rule, your fingers curl in the direction of the torque that's applied. So this B1 field is going to push the bolt magnetization down into the transverse plane. It'll keep applying that torque. It'll keep turning it as long as we leave the field on. So we only leave the B1 field on long enough to tip it through 90 degrees. We just want to get it from in line with Z to in line with the XY plane. That's all we want to do. And then we switch B1 off. So now all this bolt magnetization can see is that main static field B0, the big one that the magnet's generating. So now it's going to start to precess. Now it's going to do what that wheel did in the video. It's going to start naturally precessing around the main field. And as was demonstrated in the video, it will gradually relax and align itself back with the Z-axis over time. My terrible attempt to draw the precession motions along there. So this is, hang on, before I get to there. So once it's returned to the Z-axis, we can do this again. We can apply the B1 field along X, flip it down, let it precess, let it come back, apply B1, it comes down, precesses, and so on. While it's precessing, as this bolt magnetization is rotating in the XY direction, it's going to be cutting the coil. And as it moves through the coil, you've got Faraday induction. So it's going to induce a voltage as it rotates. And that's what we're recording when we do NMR. We're recording what's called the free induction decay. And the magnitude is going to be related to how much of that bolt magnetization vector is left in the XY plane. So I'm just not sure if people know about vectors and components and things. So if I have I should probably use a different color, but not red. So if I have my bolt magnetization vector, it will have some Z component and some transverse component. And when you do your initial flip, when you do your 90 degrees and you bring it down, you've got a maximum amount in the XY plane. And as it precesses and gradually relaxes, that's going to decrease and become less and less. So our signal will decay, and when we apply a Fourier transform, in this case we only have one frequency present, so we get one signal, which isn't very interesting, but you've got to start somewhere. In reality, we get something that looks more like that. So in this case, the time domain signal is a sum of contributions from many different frequencies. And when we apply the Fourier transform, you can see these different components represented. Now, there are lots of different frequencies present. Some peaks are stronger than others. You've got a lot of fine structure in the spectrum on the right-hand side. And you've also got this change in units. So I'm now dealing with ppm, not hertz. I'm not dealing with frequency units anymore. So this raises a number of questions, some of which I'm going to answer. So the issue of different frequencies is arising from the fact that, well, these are not just spins. These are not just bare nuclei. They have an electron cloud. There's a cloud of electrons circulating, and if you are putting these little if you're putting these atoms in a strong static magnetic field, then these electron clouds are going to start to move. You've got charged particles in a field, they're going to start to move, and then they're going to start generating their own magnetic fields. So the effect of that is you've got this B dash. In the case of a single atom, that's going to oppose the applied field, and it's going to be proportional to it. So the bigger the field, the more this shielding, this nuclear shielding occurs. And so the resonance frequency actually gets shifted because of this electron cloud. In the case of molecules, when you've got not only the nuclear electron cloud, but you've got the electron clouds of all the neighbouring atoms. I mean, for something like this, you're not just dealing with your hydrogen with its non-electron cloud, but you've got your carbon, it's got an electron cloud, you've got your oxygen and carbon, and they're going to interact. So in the case of molecules, things get more complicated. The field is not necessarily opposing it, it might be augmenting the main field. So you can get shifts in either direction. This effect is called chemical shift. You are having a shift in the frequency, the resonance frequency, because of some because of its environment. So the degree to which the frequency is shifted is symptomatic of the environment. Now this table won't mean very much to the non-chemists, but along the bottom is your scale of frequencies. So, well, I say frequencies, your chemical shift scale. And typically it's from 0 to 12. And these are all the different kinds of protons you might expect to see. So basic saturated alkanes, things like a CH3 group that I had on the board before, they'd be down the bottom, they'd be somewhere between 0 and 2. If I had an alcohol, well, one of those protons would be up here between 3 and 4. So if I see peaks at specific chemical shifts, I know approximately what kind of chemical environment I'm looking at. And this is how we define this chemical shift. This delta, this is given in parts per million. So we have this million scaling factor out the front, and we are giving this relative to a reference frequency. The reference frequency is a choice that you make when you do the experiment. Typically tetramethylsilane is, TMS is a common reference for proton. It doesn't matter, you can use something else. The point is it's relative, and we multiply it by 10 to the 6 to get the numbers into a sensible range, otherwise they'd be totally unwieldy. But this gives us nice numbers between 0 and 12 that are easy to handle. Did I want to say anything about that? No. Alright, so an actual simple example of how you do this, what it means. We can look at a spectrum of ethanol. Okay, we're all familiar with ethanol, I expect. We've got a methyl group on the end, we've got a methylene group, CH2, and there's an OH group. So we run a spectrum of this, we see something like what's presented. This is your chemical shift scale in parts per million. And we can get structural information from the frequencies where we see the signals. We can get information from the signal intensities and from the multiplet structure. So these are not just peaks, these actually have some structure. They tell us something. So this one here, this blue H, it's sitting between 1 and 2. And I said before the saturated alkanes sit down there. So that's our terminal CH3 group. And up here, between 3 and 4, well, that's the proton that's right next to the OH. That's the alcohol H. And then you have here the H that's directly bonded to an oxygen. These have structure reflecting their neighbours. So this is the N+1 rule. The methylene group has 3 equivalent neighbours. So it's split into 4, 1 to 2 to 2 to 1, but 4 distinct peaks. In the case of the blue, it has 2 next to it. 2 plus 1 is 3, so it has 1 to 2 to 1. So you can tell quite a lot based on how these signals get split. This hydrogen is labile, it behaves a little differently, as in it can exchange, chemical exchange sometimes removes these features. The other thing is if we did integrals, if we integrated the area under these, then if we compared the area underneath this peak and the area underneath this peak, then this would be in the ratio 2 to 3. So we can actually tell that there are 2 green hydrogens and 3 blue hydrogens by integrating the signal areas. So it can be quantitative, it can be descriptive, and obviously this is a very simple example. We use this to do structural elucidation for much more complicated molecules. So one of the main things that they do at Macquarie University is natural products chemistry. Lots of the drugs that we use have been developed from natural products. They find something that works really well in nature and they extract it and then find a way to synthesize it in the lab and then sell it to us for obscene amounts of money. But the first step is to go out bush, find your natural product, extract it, and then do structural elucidation, figure out what the actual chemical structure is. And this is obviously, for something like that, quite a challenge, and nuclear magnetic resonance spectroscopy is one of the big tools in dealing with this kind of thing. So this is Taxol, which is an anti-cancer drug that's derived from bark from the Pacific yew. And then another example is protein chemistry. There's a lot of protein chemists at Macquarie, and proteins are horribly complicated. And this is ubiquitin. Ubiquitin is ubiquitous. Every presentation on protein chemistry includes a slide on ubiquitin, so I had to put it in. And it's not just about what the constituents of proteins are. There are other questions that NMR can help to answer in terms of the three-dimensional structure, the folding of proteins, and which groups are actually close in space to which other groups. So the nuclei will actually interact across space, and that will affect their frequencies as well. And you can do, you can answer some quite interesting questions in that direction with NMR. So the basic steps in the experiment: you tip the magnetization from the Z direction into the XY plane. You allow it to precess. It gradually relaxes. As it's precessing, it induces that signal. We record it. We apply a Fourier transform, and we get a spectrum. But I thought perhaps, given the audience, I should say at least a couple of words about what kind of RF pulses we're using when we do this experiment. There is a whole suite of different shaped pulses that can be applied. An EBIT. Yes, there's... NMR is home of acronyms and weird things. Seduce. Yes. Solid state's better. We've got experiments like trapdoor, inadequate. There's Dumbo decoupling. That was a bit of a stretch. That's decoupling under mind-boggling optimization. People do go to great lengths to get the acronym that they want. We're even more guilty of this kind of thing than organic chemists who want to name their synthetic techniques. Anyway, lots and lots. In solution state, more often than not, we're just applying square or rectangular pulses. We do Gaussians quite often. MRI, it's mostly sync pulses. Those are just excitation profiles from Fourier transform, and the definition of a sync, in case anyone, I'm sure everybody knows what that is, but just in case. I said we mostly do square pulses, and the excitation profile for a square pulse would be a sync, and isn't that a problem? Because you get uneven excitation across the bandwidth. Well, not really. Typical 90-degree pulse, i.e. the length, the duration of the applied RF in order to tip that magnetization through 90 degrees into the XY plane, typically 10 microseconds.
So you don't measure it, you just, that's from experience, it's 10 microseconds.
You do measure it.
I guess
No,
you
you
measure
do.
it, yeah. You know
Yes,
it's
you can
which
do
node.
experiments where you change the duration and you watch, you build up a nutation profile
Right.
so that you can actually determine exactly what the, because you know, amplifiers, they get old, that will change. You can't just do it once, and it's also sample dependent as well.
Yeah.
So it'll change depending on the environment of the spin.
You tune the system to make sure you get 90 degrees or you get maximum deflection.
I will talk about that in a minute. I'm getting to it. But in terms of maximum signal, there are a couple of things. That is one of the things we need to do. Optimizing the 90-degree pulse is another. Sometimes you don't care. Sometimes near enough is good enough. You just want a signal. I said this is a very insensitive technique, but the kind of field strengths that we work at now and the kind of probes that you can work with. So there are these things called cryoprobes now where they actually cool the electronics down using liquid helium, and so the amount of noise from the electronics is just massively reduced. Signal to noise goes way up, and even though this is an insensitive technique, you know, you don't really care if you're slightly off, if your tuning's a little bit off, or your 90-degree pulse isn't quite right. It depends on what you're trying to do. If you just want a quick spectrum, is your compound what you thought it was? Yeah. But yes, the kind of amplifiers we're using, the kind of pulse lengths that we're working with, we're not going to get into this territory. And in terms of when you're doing hydrogen anyway, the range, the frequency range that you're interested in was 12 ppm. So that's, if I was using a 9.4 Tesla magnet, which is 400 megahertz, 400 hertz per ppm, so 5 kilohertz. I only care about 5 kilohertz. So, you know, even down here, I'm probably still mostly flat in terms of the excitation profile. So that's just a little bit about RF pulses. So the hardware, what is it that we actually use to do all this? Your typical setup looks something like this. Obviously you need a big magnet, and they all look like this, pretty much. Some of them aren't shiny, but the geometry is always the same. Down the bottom of the magnet, you can just about see it poking out there, and this is a blow-up of the view from underneath. You have a probe that sits inside the bore. I'll talk about the magnet and the bore and where the probe goes and all this over the next couple of slides. You can see you've got all these coax cables coming in, proton channel, oh no, sorry, that's deuterium, that's proton, that's carbon, and then you've got a general broadband channel. That's just a heater cable. Circled on the floor is the high performance preamplifier. So that's positioned very close to the probe, very close to the so that the cables don't have to be very long, so that you're minimizing losses as you're receiving signal. You're getting that to an amplifier and amplifying the signal as soon as possible. And then you have your console. This is a dual bay console. The one I'm going to show you from our system is actually a single bay, but the console's the brains of the setup. So the magnet, as the first point. In the GE video that I showed you first up, they talked about superconductivity and how you've got a solenoid which is kept super cool in order to remove the electrical resistance. So in practice, there isn't absolutely zero resistance. These things do, you do lose current over time, but it's not enough to be concerned about. For example, they checked one of the machines at UNSW a couple of years ago and it had 300,000 years left. So I'm not even worried about that. It's as near to forever as makes no difference to mortals. So you have your solenoid windings, which are kept submerged in liquid helium. So this is a schematic. This is an example of an undressed magnet, decommissioned. This is from the Geol factory in Tokyo. So the helium chamber is right in the heart of the magnet, and the windings that are used for these solenoids are typically copper-clad niobium tin, and the amount of the sort of length of winding that you're dealing with is about 12 miles or 19 kilometers of winding in order to create these solenoids. So once you charge them, that's it. There's no maintenance other than making sure that the helium and the nitrogen levels don't fall beyond a critical point. They do boil off, but they do so at a reasonably slow rate. The helium you have to top up every 3 months or so, the nitrogen every week, but the nitrogen feels very routine. Helium's a bit more interesting. If these levels fall beyond that critical point, or if someone accidentally brings a wrench too close to the magnet and you get a violent jolt, or something happens that upsets the superconducting nature of this the solenoid, then you can get a quench, which we talked about before, and there's a video on the next slide which shows you what a quench is. So yeah, why do we use superconducting magnets, not permanent magnets or electromagnets? Well, we can access much higher field strengths with supercon magnets. You're really restricted with the other two categories. These are also far more stable, and they offer us far better homogeneity in terms of the field that the sample experiences. So we talked about this chemical shift and the fact that the resonance frequency of the spins changes depending on those electron clouds. Well, if that static field isn't actually the same all the way across your sample, if the B0 value varies as you move through space, well then the changes you're seeing have got nothing to do with your sample, and they're everything to do with the fact that you've got a rubbish field to work with. So it's critical that these things are consistent to 1 part per billion territory. These have to be really, really, really good, and we need superconducting magnets to do that. All right, so yes, there's various layers. You can see there's multiple layers in here, and those are insulating layers that are dealing with the massive drop in temperature. So you're out here, you're at say 25 degrees centigrade, and then you've got this, what looks like tin foil, it's aluminized mylar, that acts as a shield. So you're shielding, there'll be infrared radiation coming off the surface of the can, and you want to shield that from heading in and heating up the cryogens. So you've got vacuum layers, you've got the mylar, you've got liquid nitrogen, then you've got more vacuum, then you've got liquid helium. So you're stepping down. 25 degrees is 298 Kelvin. So you're going from 298 Kelvin to 77 Kelvin, which is liquid nitrogen, and then you're going down to 4 Kelvin, which is liquid helium. So there's a very steep temperature gradient, so you have to have a lot of shielding in there to try and reduce the boil-off rate.
I thought 273 degrees was the 0 point.
Minus 273, yes. Yeah. So where minus 269 is liquid helium temperature. Yeah. And this is a little video that talks about quenches, which you really don't want to happen. Brooker are the main vendor that manufacture these things. This is a somewhat cheesy intro. Let's skip forward.
The electromagnet is immersed in a bath of liquid helium at a temperature of minus 269 degrees Celsius. At this temperature, the magnet is in the superconducting state. That is to say, the magnetic coil has an electric resistance which is null. To produce the magnetic field, the magnet is energized with a DC current of more than 100 ampere. As a consequence of the wires within the coils are subjected at very large magnetic mechanical forces. These forces may cause a wire section to move within the coil by fractions of a millimeter. Such a small movement in a magnetic field can produce an appropriate amount of heat so that the temperature of the wire section rises above the critical temperature of the superconductor. Hence, the wire section again shows an electrical resistance. Since the current still flows in the magnet, more and more heat is produced. As a result, the neighboring wire sections and, finally, the entire coil becomes normal conducting. The magnet coil is said to be quenched. The whole amount of liquid helium is vaporized by the heat generated in the magnet and escapes from the cryostat. In the following sequence, we can observe the quench of a 700 MHz magnet system. At the beginning, the cryostat is filled with 450 liters of liquid helium. Vaporized helium occupies 700 times more volume than in the liquid state, so that 450 liters of liquid helium corresponds to a volume of 315 cubic meters or 11,000 cubic feet of helium gas. This explains why the helium gas escapes from the cryostat with such high pressure.
I don't like showing this video because this person's just standing down there.
Yeah, probably pass out soon. Yeah.
And he's still down there.
When the magnet is quenched,
not
all
the
sections of the
magnet's
superconducting wire are correctly positioned so that the service engineers may cool down the magnet and energize it again.
So, yes, in the event of a quench, you leave. You don't wander about. Although, having said that, I did witness a mini quench, and we did all stand about going, oh, what are we doing? And taking photos, which I shouldn't admit to that. But it was only a cryo-shim, so it probably can't see, but, well, I can use the mouse, I suppose. There are some windings that are taped on that are actually, they're not going that way around, they're going that way. And those windings are cryo-shims. So you may be familiar with the word shim in terms of, in terms of like a lump of metal that you would introduce in order to distort a magnetic field. The term has carried on, but these cryo-shims are extra coils in different directions that are used to fine-tune the homogeneity of the field on installation. And if one of those quenches, then you get some symptoms which are very similar to a quench, but it doesn't necessarily develop into a full-blown quench. So you get excessive helium boil-off, you get some icing on the turrets, but it doesn't actually carry on to that full chain reaction. At least you hope it doesn't. All right, sorry, I will speed up the last bit. So the probe, that goes, I didn't actually, the bore goes through the middle of the magnet. This is at room temperature. So there is a room temperature cylindrical hole that runs through the center of the magnet, and into that goes the probe. I was going to bring one along, but I was a bit concerned about Macquarie getting cranky if anything should happen to it, so you'll just have to look at the picture and use your imagination. The probe is a tank circuit. We have an adjustable, two adjustable capacitances, matching and tuning. So this comes back to what you were saying before. We have to have the circuit actually on resonance and have to match it to 50 ohms of the coax cables. So when we do tuning and matching, we're adjusting this so that this oscillator is actually on resonance and it accumulates energy, and the way this inductance here, L, that's our actual coil. So there are a number of geometries. The most efficient implementation is actually a solenoid perpendicular to the main field, but that's not very convenient. We want to be able to drop our samples in from the top and have them sit straight down. So we have an arrangement like this. You'll have a tube that has your sample. You squirt some sample down the bottom. You have a spinner, which is used to spin the sample, which improves homogeneity in the X and the Y directions. As you spin it that way, you're averaging out any differences. And also the position of the spinner on the tube controls how what level the tube sits in the probe. So it sits right in the correct region of the coil. So we want to be able to just drop that in from the top. We don't want to have to muck about taking the probe out and sticking it in sideways or anything like that. So we don't use solenoids perpendicular to the field in solution state. You do in solids, mostly-ish. So we use we've got either a saddle coil or a Helmholtz coil orientation, and this is all part of the same. This is a blow up of what's happening down below, and this saddle coil was actually sitting on top of this Helmholtz. So you often have two observed coils. Typically you would have at least two observed coils. The outer coil would be used to observe the high frequency, high sensitivity nuclei like proton or fluorine. And this inner coil, which is going to be much closer to the sample, would be used to observe so-called heteronuclei like carbon or nitrogen, things like that. We want it to be as close as possible to the sample to get the best signal to noise. That's the console, big box. You've got the components. You've got the AQS rack, the acquisition rack. You've got a variable temperature unit. You have an amplifier, transmitter, and this thing down here is the Bruker smart magnet system, which is responsible for some things that I haven't talked about and won't talk about. So the acquisition, this rack up here is responsible for the generation of the RF pulses, and it receives and amplifies and digitizes the signal, which is first captured by this preamplifier and then directed back here and digitized. Did I want to say anything else there? No.
Fourier transforms done externally.
It's done in the software, yes. Yeah. So the console is responsible for actually acquiring the time domain signal, and then that's processed on the workstation. Okay, so finally, MRI. What's the noise all about? So there are a couple of people here who might not have had MRIs. So some of the noises, and I'll turn this down if it's horribly loud, but then it is horribly loud. So that's... This is awful. I had this done yesterday. Flare is actually not spelled like that. So yeah, you get the idea. MRI is deafening. It's not that it's much better in human scans. The preclinical stuff, for some reason, isn't as noisy, so it's not very exciting.
Just like the Russian woodpecker in the 70s.
The Russian machine.
Yeah.
So even as an operator, you have to have ear protection when you're doing this kind of work. It's deafening. So the exact, as you saw, the exact kind of sound that that you hear is going to depend on the kind of sequence that they're actually running. But the origin of the noise is actually the fact that, if I can get to the next slide, they are using gradients. So I spent a lot of time talking about how homogeneity was vital and it had to be 1 part per billion and it had to be the same everywhere. And MRI, you deliberately don't do that. You apply typically a linear gradient. You can apply it in X or Y or Z or all three. And the reason for doing that is because if you apply a gradient, a linear gradient, then if you assume that all other things are equal, and in MRI you're just interested in looking at water protons generally, it's not strictly speaking true, but mostly you're looking at water. So if you assume that all of the water protons in your body are going to have the same Larmor frequency, then if you apply a linear gradient across the person, then the exact frequency is going to be dependent on the position in space. So the reason for applying the gradients is to do spatial encoding. You can identify exactly where particular signals are coming from based on the frequency that they occur at. The frequency isn't telling you about the kind of environment, you're assuming it's 100. The frequency is telling you where that signal's coming from, and so that translates into something like that. That's my brain. That was from yesterday. So these black regions correspond to sinuses or places where there's no signal, there's no water, and then you get different kinds of contrast based on different relaxation properties. So we're talking about that precession relaxing back to the Z direction. The rate at which that happens changes depending on the kind of tissue. And so some tissues will appear brighter relative to others, and that contrast is what radiographers use to tell whether or not you've got something going on, which I don't. This is a perfectly normal brain. But that's how that works. So, the end, you'll be delighted to hear. Just some summarising points. So the MRI magnets that they use, they're about 3 times as powerful as the electromagnets in junkyards. And the magnet room is a Faraday cage to prevent that interference from external RF sources. The cryogens we work with are really cold. The main risk is asphyxiation, but you can also get cold burns working with these things. They have a very significant liquid to gas expansion ratio, hence the asphyxiation risk if you spill it. Spills are quite serious. And, the one thing I was going to say about this, they make you fill in a big long form at the beginning about have you got any implants, have you had surgery recently, have you done any metal work. They want to know about metalworking because you could have, if you had metal fragments go into your eyes or anywhere else, they need to know that before you get in the magnet, because going into the magnet can actually cause those pieces of metal to move. And so it's important to think very hard before you answer those questionnaires and make sure you're giving them accurate information. It is in your interest. And yes, the take-home message, the magnet is always on. So always treat it with respect. And other than that, it's perfectly safe. The end.
That was a 2D image of your brain.
Yes.
So I presume it can produce 3D images by the rotation, is it?
Yeah, you can do volume imaging by applying gradients in all 3 directions. Yeah. But it takes a bit longer if you want reasonable resolution.
You mentioned a button that says do not push.
Yes, the quench button.
The quench button.
Well, that quench that you saw the video, that was 450 litres of helium. That was $10,000.
Wasn't
Up in
that
smoke.
coming from the coils evaporating the helium?
I'm not actually sure how the quench mechanisms are implemented. They have quench resistors which are supposed to protect the windings. So they want a way of dissipating the current with safely for the windings, so that it's done in a controlled fashion rather than it just being out.
So you just let the helium out?
Well, in an MRI you have a quench tube, so there'll be a directed flow to the roof, and it will all be exhausted to the roof.
Oh, so that just warms up the coils?
Yes.
With the current flowing in, but then the magnetic field drops?
Yes.
Right.
Yeah.
So it's just an emergency dump of the helium?
Yeah.
So making a new hole in the ozone hole?
Don't know that helium is.
Chlorine's the problem in the
Yeah.
That's not going to
Helium's
Lowest the shear
inert, so I don't think you're going to really have any problems from helium. But yes.
Start looking on seed if you do that.
Just tapping into your electrical engineering side. So with medical MRI, they have pacemakers and things that now MRI safe.
Yes.
Do you know sort of what they do to
make
how that works? Do you think anything electrical that's going to be moving into a magnetic field is going to be inducing current?
I'm afraid you're moving beyond my my knowledge. The general, for me, if anyone comes into my facility and there's any kind of implant, I just have to say no, you can't come in, because I can't make any guesses, and I don't know enough about it. Typically, they need to know exactly what model, what part number, and they have to go and investigate it very thoroughly. But pacemakers generally it's a no-go. I didn't know there were MRI safe pacemakers.
Yeah,
So
there are.
The
So,
stainless, they're not totally magnetic.
yeah, but just think
You've got a
of
moving field.
just think of the electronics, you know, that you've got
Yeah.
wires and you're moving that through a magnetic field. That's going to induce current in the wires,
In the antenna wire sort of.
well, in any part of the circuit. So, I mean, it just amazes me that they can make them MRI safe.
that it can be done, yeah. Because with shunts and things, you worry that it's going to actually physically move as you're moving into the field. So, but it's terrible. You can fall into expectation bias. You ask people, have you got a pacemaker? Have you got any implants? Have you got this? And you're so used to people saying no, that you almost forget to ask sometimes when new people come into the facility. But I got a good kick up the bum the other day because I asked it, assuming the answer was no, and one of the people popped their hand up and said they had a shunt, and it's like, right, over there, well away from the magnets, please. So, like in aviation, expectation bias can be very dangerous in one of these places. Should always maintain good practice.
How much energy does it take to charge up the magnet?
It depends on the field. There's a 300 at the 300 solid state at New South, I think, is 35 amperes only. But you heard on the quench video that one was 100 ampere. Yeah, 100 ampere. The MRI is much bigger. So it depends. It depends on the system. But a lot of current. More than enough to kill you.
But like for a second or half an hour? I mean,
I don't actually know. I haven't been present while magnet was being brought to field. We will be getting 2 supercom magnets this year, and they will be brought to field, and I will be there for their births. Oh, I can't wait. So I'll be able to answer that question at the end of the year. But
we'll log you in for another talk.
Suckers for punishment.
CBC survives.
No problem.
When they said it took 100 amps, they didn't say what voltage though.
Zero.
Well, yeah, but you know what I mean.
But to actually charge it.
To actually charge it, like,
charge
you know, there's 100 amps and there's 100 amps, isn't there? You know,
You've got
As the
19
temperature goes
kilometres
down,
of
you don't
wire.
need much voltage.
No,
You're
probably
going to
not.
have a huge DC.
Because they're already very cold. They're already
Yeah, but
the
zero.
coils are already.
It's already super cold,
Yeah.
0, okay.
Yeah.
Lots of amps, lots of zip volts. Yeah, D cell, dry cell.
I'm a chemist, not an engineer, so.
Okay.
But they are cooled before you charge.
Why ask the killer? I was wondering how they get 100 amps into the building. You know, that would depend on the voltage they get to start with.
They bring a big box with them, I know. But I mean, the charging rods, they've got huge copper pillars on them.
Yeah.
Massive.
Yeah, they said it was 100 amps DC, but it'd be interesting to know what voltage they start.
Again, I'll be able to answer that
Yeah,
question.
we need you to come back.
Yeah.
I'm pleased that you are even entertaining the possibility.
The transmitters that you use, what is that? That's something that just a synthesizer to generate frequencies and then a broadband.
Well, I think the frequency synthesizer unit is separate. Well, the signal generation unit, the SGU, is separate to the transmitters, and the transmitters are dependent on the kind of application. So I think the one we've got is 300 watts. If you're in solids, you're up in kilowatt amplifier territory. But solids is a lot more demanding. Solids you need 2.5 microsecond 90, so you're up at 100 kilohertz. So you have to be a bit more careful about not cooking your samples. But MRI, you're not doing that. So, and they actually have a dose. They can calculate how much RF you're actually absorbing, and there'll be hard limits in the software that runs the MRI systems in the hospitals and things, so that you can't actually fry people. Yes.
A lot of people get a lot of these MRIs. Is it dangerous to their health?
My opinion is no. It's nothing like having a CT. CT, you're dealing with ionizing radiation. MR, you're dealing with, fairly mild radio frequencies. And as I say, they are controlled. The dosages are controlled. So I personally have no hesitation in doing it. When I was doing my PhD, I used to go and get an MRI and do functional MRI studies where they actually monitor brain activity while you're doing tasks. So they'll get you to do memory tasks or calculation tasks or logical reasoning while you're in the MRI, and they'll be scanning the whole time. I did that in exchange for monetary compensation quite a few times. My parents weren't thrilled about it. I was of the view that there was no significant risk.
And you used to be normal, right?
I did. And then something happened. I think it was the one at first when they were giving me propofol at the same time, and that was probably the one. They had propofol going in one arm and then blood coming out the other. They were trying to monitor my responsiveness depending on the blood concentration of this drug while I was in the MRI.
Yeah,
That was the last one I did, actually. It's 80 quid though.
It's kind of interesting because some people don't like even having a radio above the bed because the magnet is a speaker, you know what I mean? I like headphones on your head, like all of us wear headphones when we're relaxed at home and playing radio. First thing is you put a speaker on each ear.
I'm not suggesting you should do it on a weekly basis, but I have a student who injured herself, and her GP said, "Now I don't want to send you for an MRI because I don't want to expose you to the ionising radiation unless it's absolutely necessary." I'm just sitting there going, I'm not going to sit here and say it's perfectly safe. Nothing could ever happen because then I'm going to be legally liable if anything does. But if I'm being told I'm going for a CT, I'm going to want a damn good justification for why I have to go and have a CT. I want the doctor to actually have a very legitimate reason. Whereas I'm having lots of headaches. I think you should go and have an MRI. Okay.
Yeah.
You know, I don't have a big problem with that. Whereas the CT, I would want proper justification. You know, is there something else we can do first?
Drink that blood stuff.
Sorry.
The CTs I've had, blood.
Oh yeah. Yeah, all the fun stuff. They do give you contrast sometimes with them, but not always.
Injection or the contrast.
The gadolinium. Yeah.
Yeah.
Good. Thank you very much.
My pleasure.